Some common type of organic reactions are substitution, addition, elimination, radical reactions, rearrangements, and oxidation reduction reactions. Substitution and addition reaction at least may be nucleophilic or electrophilic depending on the species that initiates the attack on carbon. For example, this hydroxide may attack this carbon because it's partially positive and break this bond. As a result, chlorine will be replaced by the hydroxide. This is a substitution reaction. This reaction is also concerted. A concerted reaction is a reaction wherein bond breaking and bond formation occur at the same time. Usually, a concerted reaction is just one step. Since the attacking species in this reaction is a nucleophile, then we can say that this reaction is a nucleophilic substitution. In this next example, the double bond has a high electron density and will be attracted to the partial positive charge of the hydrogen. This bond will break and you will produce this species. The hydrogen is now bonded to the carbon and there will be a chloride ion. This is a slow step. The next step is the attack of this chloride ion to this carbon to form a new bond. This is a fast step. And you will produce a new compound. This reaction involves an addition process. HCl is added to this molecule. Since the initial attack involves an electrophile, hydrogen, we can say that this is an electrophilic addition. This process, as you see, involves two steps. Organic reactions often forms intermediates. They are transitory and reactive species in a multi-step reaction. Common intermediates in organic reactions are a carbocation, a carbon ion, and a free radical. This intermediate here is a carbocation. There is a positive charge on carbon. An example of a carbon ion is this one. The carbon has a lone pair of electrons, which gives it a negative charge. A free radical has an atom which has an unpaired electron, not necessarily carbon. On to reaction kinetics. Here we are concerned about the rates of reaction. Reaction rates are related to the number of collisions per unit of time of chemical entities with the correct orientation and enough energy to cause conversion into another entity. The overall rate of a multi-step reaction cannot exceed the rate of its slowest step, called the rate determining step. For example, in the reaction of hypothetical A and B, there may be a slow first step to form C, followed by a fast step to form D. The formation of C determines the rate of the reaction. The rate law expresses the relationship between the rate of reaction and the concentration of reactants. You can say that the rate is a derivative based on the increasing concentration of the product or the decreasing concentration of the reactant per unit of time, and is equal to a rate constant multiplied to the concentration of the reactants in the rate determining step, which is A and B. Here, the rate constant is large if the reaction is fast. We can often depict the thermodynamics and the kinetics of a reaction in a potential energy diagram, such as this one. Potential energy diagrams show reaction progress in terms of energies of the species involved. We can compare the energies of the reactant and the product. If we have Gibbs free energy here, then we can say that the energy of the product is lower than the energy of the reactant. This reaction overall is exergonic. In some cases, Gibbs free energy can be replaced by enthalpy values. If this is enthalpy, then we can say that this reaction is exothermic. This value here is called the Gibbs free energy of activation, or energy of activation, EACT. It is the minimum amount of energy needed for the transformation to occur. We need as much energy, for this case shown here, to reach the transition state. And once this transition state is reached, there's a possibility of getting towards C. Once C is formed, we need another amount of energy to reach the transition state 2. And once transition state 2 is reached, it can now go forward to the formation of D. A lower energy of activation at the rate determining step leads to faster reaction. We have two steps here. A plus B will form C, and C will form D, given that there is a higher energy of activation in the first step. We can say that the first step must be slower than the second step. If we lower this energy of activation, then the rate of the first step will increase and the reaction overall will be faster. Bond breaking contributes to the energy of activation. This is the reason why, in most cases, the first step is the rate determining step. In this step, the bond breaking often occurs. Increasing the temperature increases the fraction of collisions with energy greater than the energy of activation. So higher temperature will infuse more energy to A and B for them to collide properly and overcome the energy of activation. You often hear of catalysts. Catalysis offers a route that lowers the energy of activation and eventually increase the rate of reaction. It is difficult, if not impossible, to determine the structure at the transition state. But we need to have an idea about this structure in order for us to control a reaction. One of the concepts that can be used in this case is called the Hammond's postulate. It states that if two states occur consecutively during a reaction process and have nearly the same energy content, their interconversion will involve only a small reorganization of molecular structure. It means that, generally, the transition state looks most like the species it is closest to in energy. Because the energy of I or P is closer to the energy of the transition state compared to the energy of R. The structure of the transition state is likely to be similar to the structure of I or P. And based on this, we can say that the more stable the intermediate, I, the more stable the transition state, the lower the EACT. If we can find a way to stabilize I in this case here, the stabilization of I will also result in the stabilization of the transition state, given that they have nearly similar structure.